Dear students, in this class we will try to understand what is known as gamma ray microscope experiment. So we will discuss in this class in detail what is a gamma ray microscope experiment. Before going for this experiment, this is an experiment which is to illustrate the so-called Heisenberg's uncertainty principle. So gamma ray experiment is an experiment which proves or which illustrates clearly the Heisenberg's uncertainty principle. As per Heisenberg's uncertainty principle, we know that whenever we try to make the measurement of position and momentum of a particle like an electron, it's highly impossible. It always involves a certain amount of error. The error involved in the measurement of position and momentum of the particles which are subatomic in scale like electrons, protons and neutrons is always given by an equation known as delta x into delta px greater than or equals to h divided by 4 pi. So this equation is what is known as Heisenberg's uncertainty principle. Where what is delta x? Delta x is the uncertainty involved in the measurement of position. Delta px is the uncertainty or the error involved in the measurement of momentum. So it is found that the error in the position and the error involved in the momentum is always found to be greater than or equals to a quantity given by h divided by 4 pi. So this is Heisenberg's uncertainty principle. So we have to prove it. We have to prove it experimentally. So gamma ray microscope experiment is an experiment to prove or to illustrate the Heisenberg's uncertainty principle. Let me remind you, so this is not a real experiment. This is not a real-time experiment. This we call it what is known as a thought experiment. This is a thought experiment which is to be imagined, and using this experiment we can illustrate the Heisenberg's uncertainty principle. So the name of the experiment is gamma ray microscope experiment. Before going for this experiment, first we have to understand what is known as resolving power, a quantity known as resolving power of any given microscope. So let's understand what is resolving power. So what is resolving power? We can say resolving power is the ability of the instrument, maybe it's a microscope of any type. So it is the ability of the instrument to view two objects as separate. It is the ability of the instrument to view the two objects as separate, which are lying as close as possible. What I mean is, let's say we have two objects. Let's say we have two objects. This is one point. This is another point. We have two objects, 2 points. So we are seeing them through our naked eye now. So now it is very clear that they are separated by a particular distance. So I can see them very clearly as separate. There is no problem whatsoever. If suppose, if I keep on reducing the distance between them, up to a particular distance, I can see these two objects as separate. What is the distance? For example, if I bring the point very close here, till this distance between the two, I can still see them as separate. Means even if I decrease a little bit, still I can see them as separate. But after that particular distance, I will not be able to see these two objects as separate. Means that is the limit for my eye. To view these two objects as separate. So that particular distance, till that distance you can see the two objects as separate. That distance we call it as what is known as delta x. So what is delta x? Delta x is that minimum distance. Till that distance one can see the two objects as separate. So we say resolving power is the minimum distance. Till that distance one can see the two objects as separate very clearly. That is what is known as resolving power. So for my eye, this is going to be the resolving power. Till this distance I can see the two objects as separate. But instead of my eye, if I use a highly sophisticated microscope, and then if I try to view these two objects through that microscope, what's going to happen? We are able to see these two objects as separate even for a distance lesser than this delta x. Means with help of the compound microscope, still for a distance lesser than this delta x, we are able to see the two objects as separate. But again there is a limitation for that. Even for a compound microscope, we can keep on decreasing this distance up to a certain level. Up to that level, we can see the objects as two separate objects. But after a certain limit, even for a compound microscope, we cannot see these two objects as separate. Means even a microscope has got a certain limitation. However sophisticated the instrument may be, but still there is a limitation for the microscope till that distance you can see the two objects as separate. So that distance again we can call it as delta x. That distance for a microscope is going to be the resolving power of a given microscope. So what is the resolving power? Again it is the ability of the device to see the two similar objects as separate. Means till that distance delta x we can see them as separate. After that delta x, if you decrease the delta x value, you will not be able to, even through a microscope, you will not be able to view the objects as separate. So the microscope has got a limitation, or we can call it a resolving power. That resolving power of a microscope depends upon two important parameters. Which are those parameters? One is the lambda. You can see there is an equation here. Resolving power of a microscope is given by delta x equals to lambda dash divided by 2 sin alpha. So it depends on two parameters. One is the lambda dash, one is alpha. So what is this lambda dash? This lambda dash is nothing but the wavelength of the scattered photon. Lambda dash is the wavelength of the scattered photon. And what is this alpha? This alpha is what is known as the semi-vertical angle. So you can see from this diagram here, you can see this is angle alpha. What is angle alpha? So this is the eyepiece of the microscope. AB is the eyepiece of the microscope. Here let's say we have a point object called P. We are trying to view this point object P to this microscope to the lens AB. So if you want to view that, so what we are going to use? We are going to first focus the eyepiece on the object. When you focus the eyepiece on the object, what's going to happen? The light from the eyepiece is going to fall on the object, and then it is going to get scattered. Then out of the scattered rays, some of the rays are going to enter back into the eyepiece. So those rays which when we view through the eyepiece, we are able to see the object. Right? So this is how a compound microscope works. As a light of suitable frequency or suitable wavelength falls on the object. When it falls on the object, that light gets scattered in different directions. Out of the scattered rays, some of the scattered rays enter back into the eyepiece. Through that re-entered rays, we are able to see the object. Means what? It depends upon one of the parameters, that is the wavelength of the light through which you are incidentally light on the object. But what is lambda dash here? Lambda dash is the wavelength of the object which has undergone scattering. Means if you say this is the object, if this is the incident light of particular wavelength called lambda, but it undergoes scattering in different direction, we are taking two scattered rays. One is PB, other one is PA. So this scattered radiation is having the wavelength of lambda dash. So what is lambda dash here? It is the wavelength of the scattered photon. So any ray which enters within this PP and within this PA will be able to enter into the eyepiece. Any ray which goes beyond this will not be able to enter the eyepiece. So if we take this as an optic axis, OP as the optic axis, like the midpoint of the lens, then this angle alpha. What is angle alpha? This is what is known as a semi-vertical angle. So any ray which enters into this lens within an angle of alpha will be able to fall on the lens, and we are able to see them And again similarly here, any ray which falls to this boundary, that is the PA, any ray which enters into the lens within this angle alpha will be able to enter into the lens system and will be able to see it. So this angle becomes what is known as the alpha. So the so-called resolving power of the microscope depends upon the two parameters. One is the lambda dash, the wavelength of the scattered photon, and again one is what is known as alpha, what is known as the semi-vertical angle, that is alpha, right? So resolving power depends upon this, and this resolving power we are indicating by what? We are indicating by delta x. What is delta x? As I told you, delta x is going to be a minimum distance through which we can see the two objects as separate. That we define it as what is known as resolving power. So now we know what is delta x. What is delta x? So in this case, what is this delta x? Delta x is going to be the uncertainty or the error involved in the measurement of position. In this case, it is going to be the resolving power. So both are going to be same, because if at all you want to measure the position of that object, the minimum distance through which they are found as separate, the minimum distance, the two positions of the objects are found as separate, will be given by what? Delta x. So they have to have a minimum distance of delta x, that becomes the resolving power. Or in other words, this is nothing but the delta x, uncertainty involved in the measurement of position of the particle, what is known as delta x. And one more interesting thing here is, here we are saying it as a gamma ray microscope experiment. Why only gamma rays? Why can't the normal visible light? As we know, we are going to measure here the position and momentum of the electron. We know that size of the electron is very, very small. Since the size of the electron is very, very small, we cannot use the normal visible light. Because the electron size is very, very small. So what we can use, what we are supposed to use, we are supposed to use to view the position of the subatomic particles like electrons, which are very small in dimension. We have to go for the wavelength of very, very small amplitude, wavelength of very, very small value. So therefore we are choosing the gamma rays. We are choosing the gamma rays which are having very, very small wavelength value in the entire electromagnetic spectrum. Again, as I told you, this is not a real-time experiment. This is only a thought experiment. So we are using gamma rays because of their small wavelength, so that we can view the electrons which are having very, very small dimension. But again, the question here is, once you say we are using the gamma rays, by using the gamma rays, we are trying to find out the position and momentum of the electrons. We know that whenever we make use of a gamma ray and an electron, it's going to be an interaction between the gamma ray and the electron. So what it is going to be? It is going to be again the Compton scattering effect. Whenever a gamma ray interacts with an electron, it is going to be a Compton scattering experiment, a Compton scattering effect that we discussed earlier. What is Compton scattering experiment? We have an incident gamma ray photon. This incident gamma ray is assumed as made up of n number of photons, each carrying the wavelength lambda. When this incident gamma ray photon collides with this electron, right, there is going to be scattering. There will be n number of scattered rays. So we know that as per the Compton scattering experiment, some scattered rays will be having the wavelength same as that of the incident one. Some scattered rays will be having the wavelength lambda dash, which is always greater than that of the incident one. So the gamma ray and the interaction of electrons is going to involve the Compton scattering effect. So therefore here we are saying an incident gamma ray is interacting with the electron, of which we want to find out the position and momentum. When this collides with this, there is going to be Compton scattering. There is going to be scattering of the incident photon. So this is one of the scattered photon. A scattered photon known as a PP, which is going to enter into the lens system. Similarly, a scattered photon called a PA, which is going to enter into the lens system. What is the wavelength of this and this? This is known as lambda dash, wavelength of the scattered photon. So only those scattered photons which are traveling with an angle of alpha, that is the PA, PP, with an angle of alpha with respect to PO, that is the PA. These rays, the rays which enter here, they will be able to enter into the lens system and we will be able to see the position of the electron and simultaneously the momentum of the electron. Any ray which enters other than this angle will not be able to enter into the lens system, therefore we will not be able to see the position of neither the position nor the momentum of the electron. Therefore, this angle alpha becomes a very crucial angle, what is known as the critical angle, what is known as alpha. Right? Now we already know what is delta x. So what is left out now? We should measure now what is known as delta px. That is the uncertainty in the momentum. We have to calculate the uncertainty in the momentum. So what is the uncertainty in the momentum? So for that, we should know the change in the momentum of the photon before and after the collision. So before the collision, what is the wavelength of the incident light? It is lambda. After the collision, what is the wavelength of the scattered photon? It is lambda dash. Right? We know as per de Broglie, we have an equation lambda equals to h by t. Where lambda is the de Broglie wavelength, h is the Planck's constant, p is the momentum, I mean dB. Therefore, we can say P equals to h divided by lambda. Right? So the momentum of this incident photon is going to be h by lambda before collision. After collision, the momentum of this scattered photon is going to be h divided by lambda dash. So what is the change in the momentum? H by lambda minus h divided by lambda dash. But what we are doing here experimentally? We are measuring the position and momentum in the x direction. As you can see, in the x direction. So we are dividing this momentum component into two. One along the x direction, one perpendicular to the direction of motion. So along this direction, if you divide the momentum component into two segments, so along the x direction, the momentum component is going to go h divided by lambda into cos theta. In the perpendicular direction, it is going to be h divided by lambda into sin theta. Right? So when the incident photon collides with this, what is going to happen? This is going to lose some of its energy to this electron. As a result, we get a scattered photon having the energy lesser than the incident one or lambda dash more than that of the incident one. So change in momentum of the photon is what? H divided by lambda minus h divided by lambda dash. That is the amount of momentum the photon is going to lose. So whatever the momentum is lost by the photon is the momentum gained by the electron. What happens in the complex scattering experiment? Electron gets recoiled. And it moves with a particular velocity. Right? So whatever the momentum lost by the electron is going to be the gain in the momentum by the electron. So what is the gain in the momentum of the electron? It is going to be again h by lambda minus h by lambda dash. Whatever the momentum lost by the photon is equal to the momentum gained by the photon. So h by lambda minus h by lambda dash. If we take the momentum along the x direction, the momentum gained by the electron is going to go h by lambda minus h by lambda dash into cos theta. Therefore, we are saying the increase in momentum component of the electron along the x direction, that is due to the scattered photon along PB, means now we are focusing for the momentum along the PB direction. Why along only PB? Because any ray which goes after this will not enter the lens system. So we are focusing only the boundary, that is the last ray, that is PB. Right? That is due to scattered photon along PB. So what is the increase in momentum? It is taken as h by lambda minus h by lambda dash into cos theta. But what is theta here? You can see this is angle alpha. This angle is written as theta. What is that angle theta? This is the 90 degree, and if this is alpha value, theta is going to be what? 90 minus alpha. Theta is going to be 90 minus alpha. So if you replace this theta by 90 minus alpha, what we are going to get? cos 90 minus alpha is going to be what? Sin alpha. So therefore what we get? H by lambda minus H by lambda dash into sin alpha. What is this? This is the momentum gained by the electron due to the scattered photon which is traveling along PB direction. Similarly, we have to calculate the increase in the momentum of the electron due to the scattered photon along the direction PA. Along direction PA, right? So, if you take along direction PA, again, what is the increase in the momentum? You can see increase in momentum component of the electron along x direction due to scattered photon along PA is going to be h by lambda minus h by lambda dash into cos theta. Same as that of this. Same as that of this. But what is theta now in this case? In this case, theta is going to be, here it is 90 minus alpha. Here in this case, this theta is going to be 90 plus alpha. This is 90 degree and here you have alpha. So this is going to be 90 plus alpha. So therefore we say this theta is replaced by 90 plus alpha. What is the cos of 90 plus alpha? It is going to be minus sin alpha. Minus minus is going to be plus. So what we get? H divided by lambda plus H divided by lambda dash into sin alpha. So what is this? This is the increase in the momentum component of the electron along the direction PA. What is this? This is the increase in the momentum component of the electron along the direction PD. So now we know the momentum value along this direction as well as this direction. So why we calculate these two? Because any ray which enters the eyepiece within this direction only will be able to enter the eyepiece and will be able to measure the position and the momentum. Any ray which travels after this will not enter the eyepiece, therefore we are not bothered about them. Right? So from the equation 2 and 3, we have calculated the increase in the momentum. It is clear that any ray which travels between these two, we will be able to find out the measurement of momentum. Therefore, what we say, the uncertainty involved in the measurement of momentum of the electron will be given by the difference of equation 2 and the difference of equation 3. So if you take the difference between these two, that gives you the uncertainty involved in the measurement of momentum of the electron. Why? Because this is the increase in the momentum of the scattered photon along this direction. This is the increase in the momentum of the scattered photon along the direction PA. So if you take the difference between these two, that gives you the uncertainty in the momentum of the electron that is entering into the eyepiece. So that is going to be delta px. So once you know the value of delta px, by knowing the value of delta x, by knowing the value of delta px, we can calculate the Heisenberg's uncertainty equation, or we can evaluate this equation. So if we take the difference between these two, and we simplify, what we get is, we get delta px is going to be, differentiate this and this going to get cancelled. We are going to get 2h by lambda dash into sin alpha. It is going to be 2h by lambda dash into sin alpha. That is the value of delta px. So here we have, let's call this equation number 4. So here we know the value of delta x, uncertainty in the momentum, lambda dash over 2 sin alpha. So here the value of delta px is going to be 2h by lambda dash into sin alpha, that is delta px. If we take the product of these two, that is delta x into delta px is equals to, if we take the product of these two, what's going to happen? 2 and 2 are going to get cancelled, lambda dash and lambda dash are going to get cancelled, sin alpha and sin alpha are going to get cancelled. We are left with what? We are left with only h. So what we get? Delta x and delta px is equals to h, right? Or then again, we know that, let's call this equation number 5. We know that this value of h is always going to be greater than h divided by 4 pi. Mathematically, h is always going to be greater than h divided by 4 pi. Therefore, we can write equation 5 as delta x into delta px greater than or equals to h divided by 4 pi. Delta x delta px greater than or equals to h divided by 4 pi. What is this equation? This equation is nothing but the Heisenberg's uncertainty principle. The delta x is the uncertainty in the measurement of position. Delta px is the uncertainty in the measurement of momentum, which is always going to be greater than or equals to h divided by 4 pi. So what we got in this equation? We derived the Heisenberg's uncertainty principle by taking an experiment known as gamma ray microscope experiment. In that experiment, we measured the value of delta x, the uncertainty in the position of the particle, and we measured the value of delta px, the uncertainty involved in the momentum of the particle, and by multiplying delta x and delta px, we came to the conclusion that delta x and delta px is greater than or equals to h divided by 4 pi, which is exactly same as that of the Heisenberg's uncertainty principle. Or in other words, we derived the Heisenberg's uncertainty principle with help of the gamma ray microscope experiment, which is a thought experiment. So therefore, we say gamma ray microscope experiment is an experiment to illustrate the Heisenberg's uncertainty principle. So I will remind. So we have discussed the gamma ray microscope experiment. For that, what we did here, we calculate delta x value by using this gamma ray microscope experiment. We calculate delta px value again by using this gamma ray microscope experiment, and we found out the product of delta x and delta px, which comes out to be exactly equals to greater than or equals to h divided by 4 pi. Or in other words, we derived the Heisenberg's principle with the help of the gamma ray microscope experiment. So finally, we can say gamma ray microscope experiment is an experiment to illustrate the Heisenberg's uncertainty principle, which is a thought experiment. I think we'll stop at this point. In the next class, we'll discuss one more experiment which illustrates the Heisenberg's uncertainty principle. Till then, take care. Goodbye. Bye bye.